This circuit is designed to maintain a constant voltage level across the load resistor. Zener diode is biased at the avalanche point, where its voltage is nearly independent of the current. This constant voltage is delivered to a pair of NPN resistors connected in Darnington configuration. Constant base emitter voltage results in a constant current fed to the load resistor, and therefore a constant voltage across the resistor. The current through the lamp and its brightness is controlled by a potentiometer. At full brightness, the circuit consumes 10.2 W of power. When the lamp is completely dimmed, the power consumption is 3 orders of magnitude smaller. At 14 milliwatts, bring up the knob to adjust potentiometer wiper position. In this circuit, the transistor behaves as a voltage-controlled switch. The control voltage is applied to the gate of the transistor. When the control voltage is high, the switch closes and lets the capacitor to charge to the level of the input sine wave voltage. In this case, the output voltage tracks the input voltage. When the control voltage is low, the switch opens, such that the capacitor stores its charge, and the output voltage holds its value. Consider a P-channel and N-channel MOSFETs connected between power supply and ground. The voltage at their drains is the inverted voltage at their gates. The two transistors behave as a voltage divider. The channel resistances are controlled by the input voltage at the gates. When the input voltage is high, the bottom channel has small resistance, the top channel has large resistance, and the voltage divider's output is low. Similarly, when the input voltage is low, the voltage divider is such that the output is high. Logic circuits like this CMOS inverter are the most basic building blocks of digital circuits such as microprocessors. Note that most of the current flows when the inverter switches its state. Overclocked CPUs consume more power and dissipate more heat because they switch more often. KICME. This ring oscillator consists of 3 MOSFET inverters connected in a loop. Initially, the circuit is in the state of unstable equilibrium where all 3 voltages in the loop are at the midpoint between high and low. It takes a small amount of noise for one of the voltages. Leave the midpoint and trigger a domino effect, where the noise is inverted and amplified around the loop. With an odd number of inverters in a chain, there is no stable state to which a circuit could settle. Oscillation builds up. As seen from current animations, capacitors charge through N-channel transistors and discharge through P-channel transistors. Smaller capacitors charge quicker, resulting in higher frequency oscillation frequency. With larger power supply, transistors draw more current, also resulting in higher oscillation frequency. Make those adjustments and see how the circuit responds. Shake your mobile device to kickstart oscillation. Astable multivibrator has 2 states, neither of which is stable. It generates square waves by continuously switching between the states. Capacitors define the oscillation frequency. Astable multivibrator has 2 states, neither of which is stable. It generates square waves by continuously switching between the states. Capacitors define the oscillation frequency. Astable multivibrator has 2 states, neither of which is stable. It generates square waves by continuously switching between the states. Capacitors define the oscillation frequency. Astable multivibrator has 2 states, neither of which is stable. It generates square waves by continuously switching between the states. Capacitors define the oscillation frequency.